Hello, I'm Sean. Today I'm going to be solving Griffith's 5.8. Uh, and this question has three parts. It has to find the magnetic field at the center of a square loop carrying a current I. Find the magnetic field at the center of the square loop for any n-sided polygon of current carrying wires. And then find the magnetic field at the center of an infinity-sided polygon and make sure that it matches the magnetic field at the center of a circle. So to start, uh, essentially we're just going to be finding the magnetic field due to each of these straight sections and then adding them all together. So first we need to know how to find the magnetic field due to a single straight wire, and that'll make everything much more trivial. So to start, we start with the Biot-Savart law, um, which is our magnetic field is equal to mu naught I over 4 pi, the path integral of the source, so dl prime, crossed with our separation unit vector, not the magnitude quite yet, over our script r squared. And so just to make a quick drawing, this is going to look like this. And to start, we're just going to be considering our one script r and one theta value, and then we're going to be integrating over a range of theta values from a theta 1 to a theta 2. And this will be our height will be r because picture this as the center of the loop. But for now, we're going to be using arbitrary theta values just to get the equation. So let's start getting some of our terms. The magnitude of our dl element crossed with our script r hat is going to be dl prime sine and then pi over 2 plus theta. And we could see that from the fact that, well, so it's just going to be the magnitudes times the sine of the angle between them. Magnitude of our script r hat is going to be 1. Magnitude of our dl is going to be dl. And then the angle we're actually interested in, because our dl element is going to run along here, is going to be this angle. So the way we can get that, though, is just by seeing that our theta value here is equal to this angle here. And then pi over 2 plus this angle is just going to be this total angle that we want. We could also see, though, that because it's pi over 2 plus that angle, that's just going to be equal to dl cosine theta. Okay. This bottom we'll also define as our L prime, the total length of the wire that we're using. We can see that L prime is going to be equal to r tan of theta. And then we can then see that the differential element, or dl prime, is going to be equal to r times, and then tan theta, it's a function of theta, so we take the derivative, and that's going to be secant squared theta and our d theta. And then we could also see that just secant squared theta equals 1 over cosine squared theta. You have r times 1 over cosine squared theta d theta. Next, we're going to be wanting to find this 1 over script r squared. So we could start with the fact that s equals script r cosine theta. Once again, some simple trig. And we're going to be using r here. Because script r, this vector, projected onto the s-axis at height r, is simply going to be script r cosine theta. Then solve for 1 over script r, and we can see that's going to be cosine theta over r. And so 1 over script r squared equals cosine squared theta over r. And now we're finally ready to just plug this in to our Biot-Savart, and we're just going to be solving for the magnitude right now, and we'll worry about the direction in a second. It's going to be equal mu naught I over 4 pi times the integral, and then we're going to be varying theta from an initial theta, a theta 1, to a final theta, theta 2. So we'll do that theta 1 to theta 2. Let's just do our 1 over script r squared, so that's cosine squared theta over r. Oh, sorry, this is all squared. All right, this isn't squared, this is squared, because when we squared that, squared. And then we're going to have our r over cosine squared theta, and then d theta for our dl prime. But then that dl prime, remember we're doing this whole term, so that's dl prime cosine theta. So we have a leftover cosine theta, and then our d theta. And this mostly cancels out. And then since there's only one r on top, this r squared is not fully canceled. We can just drag that out. And then we just have a simple integral from theta 1 to theta 2 of cosine theta. And we can just evaluate that real quick. Get mu naught I over 4 pi r times, and that's going to be sine theta 2 minus sine theta 1, and that's the equation. So let's just solve, then finally get to it for one side and then multiply it by 4. So we'll call this just b1. It's going to be equal to our mu naught I over 4 pi r, and then this is a square. Maybe easier to draw this top view. You can see our theta 1 is going to be right here. It's going to be equal to negative pi over 4. Our theta 2 right here is going to be equal to pi over 4. So we're going to have sine of pi over 4 minus sine of negative pi over 4, which is of course just equal to root 2 over 2 minus, and then negative root 2 over 2, which is just going to give us root 2. So we're going to have root 2 mu naught I over 4 pi r. And then that for the total magnetic field is just going to be that multiplied by our 4 wires. So that's going to cancel out this 4. I'm just going to get root 2 mu naught I over pi r. Sorry, my pi's look like mu's sometimes. And then as for the direction, if we want our full vector, we can see that we're going to have, by the right-hand rule, with our current going in this direction, say for this right side, we can draw a little loop if we want to accentuate that. It's going to curl around it and up, and this is going to be the case for every side. It's going to be pointing up. So if we want to call this direction the z-hat direction, we could also call it the phi-hat direction for any of these Amperian loops. Just for the sake of maintaining a sort of consistent coordinate system, we're just going to call that up the positive z-hat direction. So it'll be equal to root 2 mu naught I over pi r positive z-hat direction. All right. Now the next question asks to find an expression for the magnetic field due to an n. So to do this, all we have to do is simply recognize a pattern. We could see that in a square in the center, we have this angle. These angles are the ones we're going to be using. They're equal and opposite, so we really only need to worry about this one. And in a square, the total angles add up to 360 or 2 pi. And then, so each one of these 4 angles is equivalent, and so we divide by 4 to get the, in a square that's 90 degrees, or pi over 2. But this angle that we use here is going to be half of this angle because it is bisecting it. So we can do 1/2 times our 2 pi over 4, and we'll just say this equals our theta 2, because this would be our theta 2. That would equal pi over 4, and that's what we had. You could see that for a hexagon, for example, this would maintain the case. This line bisects this angle, and so this is the angle we want. It's just going to be 1/2 of this angle, and this angle is just going to be the of all the angles divided by the number of angles, which is going to be equal to the number of sides. So it's just going to be 2 pi divided by 6 times 1/2, and we get that pi over 6 is equal to this angle. And then this would be our theta 2. So, our theta 1 would just be negative pi over 6. And so this pattern carries on, and you can see that it's just going to be pi over n. So our theta 1, our theta 2 is going to be equal to pi over n. Our theta 1 is going to be equal to negative pi over n. So we can plug that into the equation we found up here, or no, up here. And we could see that our magnetic field, magnitude at least, and it's going to be the same direction, be equal to mu naught I over 4 pi r times sine of pi over n minus sine of negative pi over n. We know that sine of negative theta equals negative sine of theta. So these negatives are going to become positive. And so we're going to have a 2 out in front. It's going to cancel with this 4. We get mu naught I over 2 pi r sine of pi over n. If we want the direction, it's going to maintain the same directionality. So our vector is going to be mu naught I over 2 pi r sine pi over n, the positive z hat direction with this orientation that we've decided on. Sorry, quick addendum. This was for one side. If we wanted to find, this would be 1 over n times the magnetic field. So for the total magnetic field, we would have an n out in front. We multiply the number of sides by the contribution from each side. So we're just going to stick an n out in front, and that is our final answer for our part B. Apologies. And so for part C, we're going to take our new wonderful equation, and we're just going to worry about the magnitude for now. And that's going to be equal to n mu naught I over 2 pi r sine pi over 2. And if we're considering an n-sided polygon with infinite sides, we're just going to be taking the limit as n approaches infinity of our expression. So the limit as n approaches infinity of our n mu naught I over 2 pi r sine pi over 2. Oh, sorry, I don't know where I got a 2 from. That's n. And we can see that this angle inside the sine expression is going to get very small as n becomes very large. So we can use a small angle approximation and change it to n mu naught I over 2 pi r pi over n. And these n's are increasing at the same rate. They cancel. Oh, and this is the limit as n approaches infinity. And these pi's are going to cancel. So the expression we get is mu naught I over 2r. And that is it. Once again, direction is going to be in the direction that we chose was up according to the figure. So that's just going to be equal to mu naught I over 2r z hat. And we can verify this is equivalent to the magnetic field due to a circular loop at the center with equation 5.41 in the book that solves for the magnetic field at distance z above the center of a loop, and it gets that B equals mu naught I over 2 times r squared over r squared plus z squared to the 3 halves. And because we're at the center of the loop, no z elevation, our z is equal to 0. And we get that mu naught I over 2 times r squared over r cubed equals mu naught I over 2r, the same expression. All right, that's our solution. And thank you for watching.